Hello everyone and welcome. I am Ismael Martinez and I will be presenting to you our work entitled RSA Over-Encryption employing RGB channels through a Steganography variant. Today we will talk about our motivation and goals, the background, some RSA and Steganography basics so it's better understood. We will discuss the proposed method, show you the results, conclusions, and future work. In this new era, information security is really important for everybody, from individuals to corporations. So, our main motivation and goal is to provide an innovative and secure method to keep our data protected. Background. As we all know, we sometimes have some information that we want to keep to ourselves, or maybe share with few others. That's why various methods through the years have been developed to achieve information privacy. Information is the most valuable resource for an organization in this new era. So nowadays, information security is a must for any corporation. Let's start with some RSA basics. RSA is an asymmetric cryptographic algorithm. This means it uses two keys, one public and private. Information is encrypted using one key and is only decryptable using the other key. That being said, we have two scenarios. Private key encryption needs a public key to decrypt and is used to make information confidential. On the other hand, we have public key encryption and it's used to prove ownership of information. So what are the keys? Keys are very large prime numbers that are chosen randomly. So now, let's talk about steganography. Steganography is a technique that is used and has been used for years to hide information within non-confidential files or messages. Information is extracted by the desired party who knows in advance that there is information hidden in the file or message. Steganography can be used to hide information within text, images, or audio files. Proposed method overview. This method is a new approach to traditional steganography. In this case, RGB channels are a medium to store data, following a set of predefined rules. Contrary to traditional steganography, no carrier image is needed, as the images are built from the data itself. As an extra layer of security, we have implemented RSA cryptography. Proposed method scheme. The flow is as follows. First, the transmitter writes the original message, which is encrypted using RSA cryptography. Then, the result is processed by the method, resulting in one or several images, which will be processed by the receiver, and this will extract the encrypted data. This data is going to be decrypted using the RSA cryptographic algorithm, resulting in the original message, which will be human-readable. So how does it work? First of all, it's necessary to decompose the data into bytes. Each byte has a value that ranges from 0 to 255. In a binary format, a byte is a group of 1 and zeros. RGB channels are bytes, which makes it convenient for the method, as each one of the bytes from original data is assigned to a channel and a pixel. In this way, we can create an image. So how is an image built with this method? First of all, it's necessary to establish proper dimensions so all the data can fit. To do this, we need to determine the amount of data stored in each pixel. In this scenario, 2 bytes are stored per pixel, so the total bytes are divided by 2. Let's see an example. The message hello has 5 letters, so it has a total of 5 bytes. 5 divided by 2 results in 2.5. But there's no such thing as a half pixel, so we need to round this to the next integer. Then 3 pixels are required to store this message. Once the number of pixels that are required to store data is calculated, the image dimensions are to be set. This method works with square images. This means that the width equals the height. To do this, we need to subtract the square root of the data per pixel. And continuing with the example, we know that we need 3 pixels to store the data, so extracting the square root gives us a result of 1.73. We need to round the result to the next integer if needed. So, the dimensions of the image are 2 by 2. The result, 4 pixels with 2 RGB channels designated to store data. This gives us 8 slots to store the relevant data, but only 5 are needed. To store data, a set of rules must be followed. For example, all rows shall store data in channels red and blue. On the other hand, even rows shall store data in channels green and blue. As of now, rules need to be user-defined. Limitations are depending on the number of channels containing relevant data. On the right, we can see a table with the possible locations to store data depending on the number of channels designated as carriers. Order is essential. Security resides on this principle. Approximations can make you lose track of the amount of data that they are sending. So, 1 pixel of the image has to store the exact amount of data that it is holding. But we need to remember the limit. Each channel can have a value that ranges between 0 and 255. So, if we are willing to hide more than 255 bytes in one image, we need to generate multiple images. In the example below, the first pixel of the image contains a channel indicating that there are 255 of relevant data hidden within the image. So let's talk about the security. As stated before, the order in which data is saved into an image is extremely important. The number of possible ways to store data is defined as 3 multiplied by the factorial of the number of pixels. The number 3 is because we have 3 layers: red, green, and blue. Multiple images add more complexity. Guessing the correct pattern is far too complex, as the probability is 1 divided by the number of possible ways we can store data. In the example below, we have an image that is 12 pixels wide and 12 pixels tall. If we apply the formula, we have 1.86 multiplied by 10 to the power of 24 possible ways of sorting pixels and RGB channels. The results showed that the time it took to process data into an image was at most 30% slower compared to a single RSA encryption decryption process. The size of the resulting images were 20% the size of traditional stego images hiding the same data. Also, the method has a linear complexity. This means that the more data it has to process, more time it will take to complete the hiding process. Conclusions and future work. The method shows the independence of carrier images, contrary to traditional steganography. The time it takes to complete the process, RSA plus the method, is higher, making it necessary to think of improvements. The resulting image's weight is significantly smaller to traditional stego images, making it suitable to hide considerable amounts of data. As future work, we plan the implementation of pseudo-random method, which selects which layer and pixel will contain relevant data, making it more safe. And that's all for today. Thank you for your attention. My name is Ismael Martinez, and if you have any questions, you can email them to the mail below.